Hello everybody. Now we are going to solve a problem to find out this Q point or the quiescent point for this BJT. So this is bipolar junction transistor. This is BJT. Since here we have this arrowhead outwards, this indicates it is a NPN transistor. So now we are going to mark the terminals. So this is the collector. This would be emitter, this is the emitter, and this is the base of this transistor BJT. And this Q point or operating point is nothing but IC and VCE. At the quiescent point, it is taken as ICQ and VCQ. So IC is the collector current which is flowing through this RC resistance, and VCE is the voltage across this collector to emitter terminal. So we need to find out this collector current and the VCE, that is collector to emitter voltage. Okay, let's get started. For this, first we need to find out this VB, and this VBE value is known to us. It is given in the problem itself. Otherwise also we know that for the transistor to be in the active region and to make it on, this must be 0.7 volts for silicon. And this VB is the potential or the voltage of this base. So it is the base voltage with respect to ground, isn't it? So this is the voltage measured from this base to ground. So to calculate this, we look at this biasing network, and this is your biasing network for this transistor. So this is nothing but voltage divider bias. So we need to use VDR, voltage divider rule, to find out this VB. So this VB is equal to the supply voltage. So this VCC will be available here also at this point also, isn't it? So VCC multiplied by resistance of this across which this VB exists. So it is RB2 resistance divided by the total resistance of this voltage divider biasing. Okay, so it is RB1 plus RB2. So this VB is equal to VCC is 15 multiplied by this RB2 is 55 kilo ohm. So it is 10 power 3 divided by this RB1 plus RB2. So it is 110 plus 55 into 10 power 3. So this is equal to 825. This 10 power 3 can be cancelled, divided by 165. So this value is equal to 5 volts. So VB is equal to 5 volts. That can be taken as VTH, the Thevenin's equivalent voltage. Thevenin's equivalent voltage. We need to similarly find out what is RB, the equivalent resistance. So that RB is nothing but the parallel combination of this RB1 and RB2. So it is equal to 55 kilo ohm in parallel 110 kilo ohm. So how would you calculate this parallel combination value? So it is 55 into 110 divided by the summation of both, right? So 55 10 power 3 plus 110 into 10 power 3. So this is equal to 6050 into 10 power 6 divided by 165 into 10 power 3. Cancel out this 10 power 3. And here you will be getting this as 36.67 kilo ohms. So this is your RB. So once we found out this value, we can replace the circuit. So now we got this modified circuit with the equivalent Thevenin's voltage and the Thevenin's resistance RTH, which is nothing but now this RB, equivalent resistance. Okay, so these two values are here being substituted and we got the new modified circuit. So for this side we are going to write the KVL equation for the input side. So this is your input side. So for the input side we are going to write the KVL equation, Kirchhoff's voltage law. So when you start from here, it is minus VTH. Then here the current which is flowing here is IB current. So it is plus and minus. Entering current point is plus. So it is plus IB into RB. Then between this base and this emitter, we have this VBE. It is also plus and minus. So it is plus VBE. Then here the entering point for this current IE through the resistor RE. It is plus and minus. So it is plus IE RE. Then we come to this ground, isn't it? So that is equal to 0. So this is our input side KVL equation. Now we can substitute the values for this. So it is minus 5 for VTH plus IB value that is not known to us. RB value is 36.67 into 10 power 3 because it is kilovolt. Plus it is zero point 0.7 volts for this VBE plus IE value is not known. So it is IE multiplied by this RE value is 6.8 kilovolt to 10 power 3. That is equal to 0. But we know this IE and this IB are related with this equation 1 plus beta times IB. And this beta value is given as 100. So it is 100 plus 1, that is 101 times this IB. So in place of this IE, we can substitute this, isn't it? So now we got the new equation. So now we got the new equation as minus 5 plus this 0 0.7 will give you minus 4.3 plus 36.67 into 10 power 3 IB. Then here this IE can be replaced by 101 IB, isn't it? So it is plus 101 IB multiplied by the 6.8 into 10 power 3, that is equal to 0. So when you combine these two IB values, we'll get it as 723.47 into 10 power 3 IB, that is equal to 4.3. So IB is equal to 4.3 divided by this 723.47 into 10 power 3. So we get this IB as this is equal to 0.00594 into 10 power minus 3. So we can rewrite this as 5.94 into 10 power minus 6. So what is the answer for this IB? IB is equal to 5.94 microamps. So one answer we got for IB. But what we actually require, we need only IC. So how to calculate IC now? What's the relationship between IC and IB? IC is equal to beta times IB. Okay. So 100 into this IB. IB value is 5.94 to 10 power minus 6. So you get this as 5.94 into 10 power minus 4. 0.594 into 10 power minus 3. Okay, 0. So it is 0.594 into 10 power minus 3. So IC is equal to 0.594 milliamps. So we got our answer here. So we have calculated IC. First answer we got. So with the same circuit, we are going to write the output side equation, KVL. At the output side, we are going to write the KVL. So it starts from here and ends here. Okay. So starting from here, we can write it as 15 minus this ICRC minus across this, we will be getting VCE, isn't it? And we know that the current flowing through this RC is IC. The current which is flowing through this RE is IE. Okay. So for this portion, it is ICRC. And for this portion, it is minus VCE. And then for this portion, it is minus IERE. That is equal to 0. So this is the output side equation. So this is the output side equation. So now we can substitute the values wherever possible. So IC value we have calculated just now as 0.594 into 10 power minus 3. RC values here it is 4.3 kilo ohms, so it is 10 power 3. Minus VCE, we don't know this, which is to be determined by us. And IE value is nothing but 1 naught times IB value, isn't it? So 101 into that IB value is 5.94 into 10 power minus 6 multiplied by this RE. RE is 6.8. RE is 6.8 kilo ohms, 10 power 3. That is equal to 0. Now we can simplify this. This two get cancelled out. They get cancelled. So it is 15 minus 2.5542 minus BCE minus this 101 times 5.94 into 6.8. So there we get this is 4.079. That is equal to 0. So from this we'll get the answer for this BCE as 8.371 volts. So this is our second required answer. So to get the operating points, the Q points is therefore found out as ICQ. You have to rewrite this as ICQ, that is 0.594 milliamps, and this BCEQ, that is equal to 8.371 volts. So we got the answer. Okay, hope you have understood. Thank you.